So in the previous video set, we saw the critical value method, and the critical value method could be used to find the optimal, either maximum or minimum values of functions on their graphs, as well as some other types of word problems. Another approach that could be easier in some instances is using these things called Lagrange multipliers. And what a Lagrange multiplier is, it says that there's a constraint function or a secondary function to where g of xy is equal to c, right? So there's like basically some sort of constraint going on to where you can't exceed or you can't go under some specific value. To optimize the function, what we're going to do is we're going to look at the intersection of those curves, and we're going to take a look at see where the normal vectors occur to those curves. And where those occur, those are going to be the optimal values given the constraint. All right, so if you can see in this diagram, that gives you a pretty good indicator of what's going on here. So the one that's in red, the line that's in red, or I'm sorry, the curve that's in red, excuse me, that's the one that's going to be the constraint function. And then there's a whole bunch of other functions going on, or I guess at least some sort of constants that those are equal to. And we're just trying to find the constant that gives you the optimal normal for that, okay? And so what we do is we take the gradient of f, and we're going to set that equal to a gradient of g times this lambda, all right? So it's true for some lambda, we don't know what that lambda is, right? But if we can find that lambda, then we could try to find the scalar to which it makes it valid. In other words, we can find where that's, normal is going to be perpendicular. All right, and so to be able to use Lagrange multipliers, we get a system of equations. So we have a constraint function g, we have a function that we're trying to optimize f, and all we're trying to do is we're going to take the partial of f with respect to x, set it equal to the partial of g with respect to x multiplied by lambda, and the same thing for y, and then if it's a 3-variable function for z as well. And the function, the constraint function g, x, y, z is equal to some constant k, which really doesn't matter. It could be anything, but we are going to use the constraint function to find those optimal values. Okay, so hopefully that's an overview as to what Lagrange multipliers are. It's just basically a curve intersecting another curve at right angles, all right, to find the normals of those. And there's going to be some lambda to give you the optimal value of that. So let's just take a look at a couple basic examples of using Lagrange. We'll start out with a two-dimensional example. And let's say we have this function fxy equals e to the xy, and it's subject to the constraint that x squared plus y squared is equal to 8, and we're trying to optimize those values. So in other words, what values on this circle, x squared plus y squared equals 8, are going to optimize f of xy equals e to the xy. Okay, this is actually a very common type of problem in business where you have a multivariable sort of structure and you have a constraint put on that structure. For anybody that's studying actuary science, this is going to be something that you use all the time. All right, so let's define our functions. All right, clearly f is this function here. G is just going to be x squared plus y squared. All right, so we ignore the 8. All right, it doesn't matter what the 8 is for now. And remember what we're trying to do is we're trying to find f sub x such that it's equal to lambda g sub x, and f sub y which is equal to lambda g sub y. So we need to find the partials. Fx is really easy. That's equal to e to the xy multiplied by the derivative of xy with respect to x, which is y. Now, lambda g of y, so lambda g of x, lambda g of x is just going to be 2x, but then we also have to multiply it by the lambda. And so these two have to be equal to one another. All right, so that's actually just substituting back in here. We're going to do the same thing for fy. All right, fy is going to be x e to the xy. And then lambda g sub y, or gy, is going to be 2y lambda. And what we get is we get a system, right? Just like we did before. So how do we solve this system? Well, there's a number of ways to do this, all right? One thing that we notice that's common between the two is lambda, all right? So we could solve for lambda and then substitute. And we could do that fairly easily. We could solve for e to the xy and then substitute. So let's just solve for lambda of fx. Okay, so y e to the xy equals 2x lambda implies that y e to the xy over 2x is going to be equal to lambda. And so how does that help us? Well, we can substitute back in for lambda in fy and see what happens. So if we do that, then that means that fy becomes x e to the xy is going to be equal to 2y, and then we're going to multiply that by what we just got for lambda, y e to the xy divided by 2x. All right, so how does that help us? Well, notice that on both sides, well, there's a 2 here that we can simplify. There's also an e to the xy that we can cancel out. All right, so that makes it a little easier. So now we're going to have x equals y times y, which is y squared over x, not x squared, just x. And so if we multiply both sides by x, the relationship that we get is that x squared is equal to y squared, or in other words, x equals y. How does that help us? Well, remember earlier we had this constraint that x squared plus y squared must be equal to 8. So we can substitute into the constraint. And if we do that, x squared plus y squared equals 8 becomes x squared plus x squared equals 8, which means that 2x squared equals 8, which means x squared equals 4, which means x equals plus minus 2. All right. And of course that helps us because then we can solve for y squared. We can just back substitute here. So we get plus minus 2 squared plus y squared equals 8. And that means that 4 plus y squared equals 8. Clearly, y is going to be plus minus 2 as well. So y squared equals 4, which implies that y is equal to plus minus 2. And so what does that mean? That means that there's 4 potential optimal points, all right? Because when x is plus minus 2, that means that y is plus minus 2, okay? So there's 4 optimal points. And the 4 optimal points are 2, 2, negative 2, 2, negative 2, negative 2, and then finally 2, negative 2. How do we figure out which ones are the optimal points or which ones are the biggest and smallest points? Well, we just plug them all back into the original function, all right? So these, the 2 and negative 2, etc., those are all the biggest points, okay? The question at this point is which one are max and which ones are mins. So let's figure it out. So we're going to find the original function at 2, 2, the original function at negative 2, 2, the original function at 2, negative 2, and then surprise, f at negative 2, negative 2. So this would be e to the 4th. This would be e to the minus 4. This would be e to the minus 4 as well. And then clearly, this is going to be e to the 4th power as well. So negative 2 is e to the positive 4th. All right, so it looks like that the maximum possible value is e to the 4th power, given the constraint. It looks like the smallest possible value, all right, is going to be these values. All right, so these are the min. All right, so what we can say is that there are max at the points 2, 2, e to the fourth, negative 2, negative 2, e to the fourth. There are min at 2, negative 2, e to the minus 4, as well as negative 2, 2, e to the minus 4. All right, so that's an overview as to what the Lagrange multipliers can do. All right, so subject to some constraint, we can go through and be able to evaluate maximum and minimum values. We could do the same thing in 3 dimensions, which we're going to look at in the next video, and then we're going to take a look at some applied problems as well.